This video is to discuss an overview of the purification of the alcohol that you isolated at the end of your two-step reaction process, which is, recall, you took an alkyl benzene and did a Friedel-Crafts acylation reaction, which is, recall, an electrophilic aromatic substitution reaction. You then took the product you isolated from that Friedel-Crafts acylation and reacted it with phenyl magnesium bromide in a Grignard reaction to give you this alcohol product. Now, hopefully, you have in the analysis, and we saw from the NMR last week, what you have is primarily the alcohol product. However, you've also got in your alcohol product some unreacted ketone and definitely some biphenyl, which is a byproduct of the Grignard reagent reacting with bromobenzene. And so how are we going? You saw this in the TLC, and how are we going to get these three different compounds apart? Well, one of the properties that we can use here is we can use the polarity of the compounds to separate them. So, for example, the alcohol, because it has the OH group, can undergo hydrogen bonding, and therefore it is going to be the most polar, whereas the biphenyl has only nonpolar carbon-hydrogen and, not hydrogen-hydrogen, sorry, carbon-carbon bonds. And so that means it is very nonpolar. And in the middle we have the ketone, which has the dipole-dipole interactions present because of the polar carbon-oxygen-carbonyl bond. Okay. So you've already seen that you can separate these compounds using thin layer chromatography, or TLC, but that's an analytical technique. That just tells us whether we have the compounds present or not. And what we're going to do this week is we're going to take that mixture and we're going to separate it using a technique called column chromatography, which actually allows us to isolate the different components in the mixture. Recall from thin layer chromatography that more polar solvents move the molecules more on a TLC plate. In other words, the molecules will have a higher RF value. And less polar solvents move the molecules a little less, and so they have lower RF values, and that's how we get separation. Now, we're going to use a combination of solvents, specifically nonpolar hexanes, mixed with a little bit of ether, specifically diethyl ether, which is more polar, and therefore that's going to allow us to separate the compounds. And it's very, very common in TLC, as you've seen, and in other applications, to use a mixture of nonpolar and polar solvents. One of the most common mixtures that's used is hexanes along with ethyl acetate, which is pictured here. But the ether is nice because it's very volatile and easy to get rid of. Okay, so recall your TLC analysis of the crude product of the Grignard reaction. This is a bit idealized. For one thing, your compounds weren't different colors like I've pictured here, and probably your ketone and your alcohol weren't quite that well separated. They were running a little closer together. And as I said in the previous slide, the solvent you used is 10% ether and hexanes. Now, if we wanted to get a pure sample of our alcohol, we could, actually take a spatula and scrape the spot off the plate and then filter it with some solvent to get it out. And there's actually a technique where you do that that's called preparative TLC, but that's not what we're going to be doing, and it's kind of a pain. So instead, what we're going to be doing is we're going to be using a technique called column chromatography to purify our sample. Recall that in thin layer chromatography, the TLC plate is coated with an absorbent layer of something called silica gel. And in column chromatography, what we do is we have a glass column that is packed with an absorbent. Here the absorbent is alumina, but we are going to use silica gel as our absorbent. So what you do is you pack this glass column with silica gel and you add solvent to the column. And the solvent flows through the column, and as it flows through the column, it brings the compounds with it. And what we see here is, recall the biphenyl, which is the lowest polarity, and therefore it's going to have the highest RF value on a TLC plate, which means that it's going to come off first. So as the solvent is flowing down, you can see it coming off here, and eventually it ends up in our collection vessel. Alright, so once the compound with the highest RF value is eluted, then the other compounds are going to start coming off, and notice this is now showing the ketone, recall, which is slightly more polar because it's got the polarized carbonyl bond. So that's going to be the second compound to come off. And then finally, the last compound to come off is going to be which is the most polar because it has this OH bond here. Okay, so then once the alcohol has come down the column and collected, now we have all our fractions, and what we have to do is, because recall, there isn't actually any color, so we really can't tell which fractions have our components in them until we actually analyze them using TLC. And so here you can see an analysis of the first 6 fractions on 2 different TLC plates. And you can see fractions 1 and 2 contain biphenyl. Fraction 3 contains both the ketone and the alcohol. And fractions 4 through 6 contain only the alcohol. So what we would do is we would combine fractions 4 through 6 and rotovap that down to isolate our product. So here's a brief overview of what we're going to be doing. You're going to use a short pasteur pipette as a column. You're going to pack it with silica gel, apply 50 to 60 milligrams of your crude product. You're going to elute it with the same solvent. The same solvent is for TLC, the 10% ether and hexanes, and we're going to collect 10 fractions. Then you will analyze each fraction by TLC, combine the fractions with the alcohol product, rotovap those, and analyze them by NMR. And I'm going to have a separate video that's going to discuss the process of doing all that.